Alright, guys. Last section in Chapter 5. I don't know about you, but I'm excited to get finished. We're so close to the end. After today, we'll have a test for Chapter 5. We'll do a couple of quick pieces of Chapter 6 and Chapter 7, just things that occasionally show up in the AP exam, just kind of final pieces. And those will be all that's on your final. I don't plan on having anything from Chapters 1 through 5 on your final, so your Chapter 5 test will be over Chapter 5 material. Your last test will be over the little pieces we talk about. I'm going to try to have videos for those pieces posted on Sunday. That way those of you that are taking the AP exam can take a look at those before the AP exam and get those done if you wish, so that way you're completely done. And those of you that aren't can go ahead and start early and get the things finished. And I'll post a test sometime in the middle of next week or possibly the end of next week. So, Chapter 5.7, Inverse Trigonometric Functions and Their Integrations. To finish with this chapter, so far in this chapter we've talked about logarithmic functions and how to integrate them. You have your standard power functions and how to integrate those. We talked about the properties that fit those two together. We talked about inverse functions. We then talked about inverse trig functions, and how to integrate those trig functions is our last piece to put this chapter together. This will conclude the major basic rules to integration, which concludes the majority of what we have to talk about for calculus. So let's talk about our last theorem. Woo! Theorem 517. For this theorem, you'll notice that this one's shorter than Theorem 516. Theorem 516 had 6 parts, one for each of the 6 inverse trigonometric functions. Notice that for this one, there are only 3. The first one, notice that these are all written in du form. So we had du over the square root of a squared minus u squared equals arc sine of u over a plus c. Number 2, integral of du over a squared plus u squared equals 1 over a times arctan of u over a plus c. And number 3, integral du over u square root of u squared minus a squared, which is equal to 1 over a arc secant of the absolute value of u over a plus c. So, these pieces, you'll notice there's only 3 of them, first of all, sine, tangent, and secant. The reason being is there's no natural forms to integrate the other 3 derivatives. There's no good way to integrate arc cosine. There's no good way to integrate arc cosecant or arc cotangent. They don't integrate well. And so these 3 are the last ones we have to talk about. And to do these 3, we're going to look at some examples, and that'll pretty much finish us out with the chapter. So this is pretty much it. In the text, you'll notice that I am skipping over one little piece. It's not required for us to talk about. The reason being is because, well, completing the square isn't really discussed on the AP exam. And so if you want to take a look ahead, you can look at example 4 and example 5 to see some nice little ways you can integrate more functions using completing the square. But they're not really covered for us, and so we kind of just skip them out. At the end of the section, you'll see these basic integration rules, which is a summary of all the integration rules we've had so far. The similar summary is in the front of the textbook, which is pretty nice, and so make sure you have those. And now let's look at some homework problems. Let's start with number 2. Okay. So the trick with these kinds of problems, and the trick with all of your problems tonight, is going to be trying to see which types of problems you're dealing with, and to see which of these 3 forms they're going to be in. And notice there's an easy way to tell. You have just the roots for number 1, the root with a variable in front for number 3, and no root at all for number 2. And so in general, you can kind of figure out which one it's supposed to go with just by kind of eyeballing it. The trick is to try to figure out what a and u are going to be. Because if you can figure out a and u, you can just plug into the correct function, and then you're done. So in number 2, I have the following integral. The integral of dx over the square root of 1 minus 4x squared. Well, in this case, I see that I have a square root, so I know it's got to be either number 1 or number 3. I notice that I have nothing out front, whereas number 3 requires there to be a variable out front. And so I'm going to assume we're supposed to use number 1. But then if I want to use number 1, I need to figure out what's a and what's u. Well, in this case, a, remember, this is supposed to be of the form a squared minus u squared. So in this case, I can tell from the picture that if we have 1 equals a squared and 4x squared equals u squared, I can do some simple math to figure out what the a and u should be. So in this case, a should be 1. Take a square root of both sides. And u, square root of both sides as well, should be 2x. So now I can use my first rule with a is 1 and u is 2x, and I can plug in. So we assume this integral is going to be equal to the arc sine of 2x over 1 plus c. There it is. So it's a basic situation of, do you understand how these three interact? Can you figure out the pieces that go into them? And then it's a plug and chug integration, which is nice. Let's go with number 4. Same process. So number 4, we have the integral of 12 over 1 plus 9x squared dx. Okay. So in this one, I can see that it matches one of my forms here. In this case, there's no square root, so it looks like number 2. And just like with number 2, I want to figure out what a and u are going to be. But before I do that, you might notice there's something that is not in number 2 that is in this problem. On number 2, on top, we just have du, meaning there's no constant. But on this one, we have a 12. Don't forget your integration rules. We can always move that 12 out front. And now this looks a lot more like number 2. And so from here, we have to do the same basic process. We want to have a squared equal 1. We want to have u squared equal 9x squared, which means that our a has to be a value of 1. Our u has to be a value of 3x. And then we can just plug in. So we take 12 times, because remember that 12 is not a part of the integration process. It stays on the outside being multiplied. So we take 12 times this number. So this says 1 over a, which is 1, times arctan of u over a, which would be 3x over a, plus c. Now, we should simplify what we can here. 1 over 1 is 1, times 12 is 12. Arctan, 3x over 1 is just 3x, of course, and then plus c is plus c. On the top one, yeah, we probably could have done 2x over 1 is just 2x. It's kind of up to you. So there you see how we just kind of figure out which pieces go into the formula, and then it's a plug and chug problem. The major differences come when it's a different kind of problem. And so I want to take a look now at number... Let's look at a couple of these. These are good ones. We're going to do number 12, 16, and 20. We're going to do 12, 16, and 20. Okay, so 12. On number 12, we have the following function. It states the integral of 1 over x square root of 1 minus ln of x squared dx. In this case, you might be looking at this and be like, we got a square root with an x in front. This looks clearly like number 3. As it turns out, that's actually wrong. That is because at first we need to do a u substitution. The u in this case I'm going to choose as ln of x, which means my du is 1 over x dx. Now you might notice in this problem, we actually have that in the problem. We have a 1 over x and we have a dx. Here's our 1 over x, and there's our dx. So this piece is just going to be replaced with du. This becomes the integral of 1 over the x, the 1 over x and the dx are going to be absorbed in du. The ln of x is going to become a u, so we have the integral of 1 over 1 minus u squared dx u. Like so. Oh, that's a little light. Dang, I forgot this pen does that. Okay, let's try this one. Integral of 1 over big square root 1 minus u squared du. And now from here, you might notice this looks a lot like our number 1. It's because it is like number 1. And so it can be tempting to look at these problems and be like, I clearly see the connection, but in reality, you may have to do some changes first before that connection is actually right. So in this case, once we recognize this is just our first one, this becomes arc sine of u over 1 plus c, and then we make sure our u is ln of x, so this becomes arc sine of ln of x plus c. And there we have it. So, for each one of these, the trick is figuring out which of the rules from past and present actually applies. And to see that we are always allowed to do things like use substitution to create a different problem, and to rewrite the problem using those forms. Now let's talk about 16. Pen's starting to bleed. Alright, 16. We have integral of sine of x over 7 plus cosine squared of x dx. Okay, at this point, you may be looking at this and going, well, this doesn't really fit any of our forms. Well, that's not quite true, because if I choose a u, I can do a u substitution, and the u I'm going to choose is cosine of x. The reason being is I know my du is equal to negative sine of x dx, and I have sine of x dx in the problem. So I pick a u, remember, that has that piece, the du, in the problem. The only difference is there's no negatives, so I'm going to make this negative du equals sine x dx. And now I can do a direct substitution. This becomes the integral of negative du over 7 plus u squared. Now, this looks a lot like our second shortcut here from our theorem 517. So in our second shortcut, we have a du on top. That negative can pop out front. In this case, our a is going to be the square root of 7. Rewritten like this. And so now we can just use that simple shortcut to plug in. Don't forget, though, we do have a u in the problem. We have to make sure we get back to being cosine of x at the end. So we use our second shortcut, which states we do 1 over a, so we 1 over the square root of 7, arctan of u over square root of 7 plus c. And now make sure we do not want u in this problem. We want to make sure we have x in the problem. This becomes 1 over square root of 7 arctan of cosine of x over the square root of 7 plus c. Unlike with things like Stancil's class and some other teachers, you are fine leaving the radical down in calculus. Don't forget that. Just make sure you end up with the same function when you started with in terms of x. Let's look at number 20 as our final problem. We'll do together. All right, number 20. For number 20, we have... Oh, sorry, I wanted to do 22, not 20. 20 is pretty straightforward. It's just, looks a little funky. Okay. For 22, we have the integral of 4x plus 3 over the square root of 1 minus x squared dx. Now, with this function, you may note that in this function, it looks like a u substitution kind of problem, but the derivative isn't in the solution. Because if I choose my x squared minus x to be my u, well, then I would expect to see 2x or some variation on that, but I have 4x plus 3. That plus 3, there's no plus 3 or multiple of 3 inside of this derivative, and so that's not looking good. You might also notice that this bottom piece fits one of our forms. It looks like number 1. And so, like, it's close, but it has this 4x plus 3 on the top that isn't going to work. And so don't forget, one of the things you can always do with things like fractions is you maybe write them. I can write this as the integral of 4x over square root of 1 minus x squared dx plus the integral of 3 over the square root of 1 minus x squared dx. This first one now is solved by simple u substitution. We let our u equal 1 minus x squared. We'll get a variation of this, and then we can use u substitution to fix the answer. And over here, well, this is just using our first shortcut. With the 3 on top, we pick the 3 outside. It's pretty straightforward from here. And so in this kind of problem, you're always allowed to take a different approach if it means that you can do the problem. And so for this one, I'd have the integral of 2 1 over the square root of u du. And for this one, I would have 3 integral 1 over the square root of 1 minus x squared dx. This first one, when I integrate, I would get negative 2 u to the 1/2 power divided by 1/2 du, well, not du, plus 3. And this would become, the 3 is the arc sine. And now everywhere there used to be a u, I can replace back with this 1 minus x squared. This becomes negative 4 1 minus x squared to the 1/2 power plus 3 arc sine of x plus c. And so don't forget that for many problems, you can look at old techniques and old ways of doing them. The new ones are meant to fill in gaps. They're not meant to replace. And so while this one, part of it can be done with the old ways, part of it can't. And so on the whole, this problem is impossible, even though pieces can be solved. But with this new information that we have from 5.7, we can actually solve both pieces, meaning this is now a solvable problem. I do want to note one last thing. Your last couple of problems are all just dealing with plugging them in. That's not too bad. It's these ones. And so I want to go through these real quick, and this will be the last thing I talk about. These are 3 very similar looking integrals. But notice that 2 of them are solvable. This first one is solvable by using arcsecant. The second one is solvable by doing a u substitution. But the third one isn't solvable at all. There's no basic rule that will fix this problem, because it's x squared minus 1 instead of 1 minus x squared. Like I said, Theorem 517 is very specific. It only allows us to do these 3 very specific things. If it's not in this form, we can't do it. And so C isn't in that form, we can't do it. There's no way to rewrite it to make this work. There's no fancy substitutions you could do unless you're willing to look at imaginary numbers. And I don't think you guys want to do that right now. So that's actually how you solve C, in case you wanted to know. This one, same thing. Like, these are 3 very similar looking integrals, but 2 of them can be solved, 1 of them can't. The first one can be solved by doing a simple u substitution. You know, and you let ln of x be your u, and then the derivative would be 1 over x, which you have, and then you can get ln of the absolute value of ln of x plus c. And so the first one can be solved. The second one can also be solved by a different u substitution. Okay? Where you have ln of x as your u, this becomes u squared over 2. Yeah, this becomes a simple problem. But c looks very similar to these 3, but it actually looks the easiest, but it's not solvable. I mean, look at this list of integration rules. There's nothing that deals with the integral of ln of x. That's because there isn't one in the natural numbers. You have to look to imaginary stuff. And so anytime you talk about these functions, there's limitations that you're not going to get to unless you go farther. If you have questions about where things come from, the biggest thing I can tell you is, well, you need to go farther. There's more advanced things you can learn and more advanced things you can do with these functions that just can't be done right now. This will conclude Chapter 5. I'll be posting a review tomorrow during the day. and posting our test probably tomorrow night, giving you a couple days to work on it. Next week, we will have our last major sections. One section from section 6 and two from section 7. Chapter 6 and chapter 7, respectively. And that'll end us for the year. Good luck to those that are taking the AP exam, in case I don't talk to you between now and then. Do your best. Don't worry about what your score is. I know that's easy to say because, I say that to everything, but the score does not reflect your ability. It only reflects your score. That's the best thing I can tell you. And so I hope you guys have a good weekend. I'll make sure that review gets sent out, and I'll see you guys next time.